ladies and gentlemen. Thank you for coming this morning to have it early to listen to my lecture on the logical inconsistencies of the special theory of relativity. Einstein wrote a paper in 1905 that is heralded as a turning point in our understanding of the nature of space, time, and the universe. It's true in a sense, but in the reality, it's unfortunate because it's introduced an element of mysticism into physics. So although it did have this effect, it's been quite a disaster for science. So first I'd like to start off with a bit of a discussion on dimensions and units, because they're quite different. If we call time t, well, we can measure the time t in any kind of unit. We could use it in seconds or years, or hours and days. And length, if we call length L, but we don't worry about the actual units that we use. We just talk about length, and we denote it by L. And we can measure that in meters, feet, and light years, or inches. And we have, from our common experience, 3 length dimensions: length, breadth, and height. For instance, in a box, we have the length of the box, the width of the box, the height of the box. Now, the obvious thing about it is that if you have a length, can you add to it a time? Hello? Oh, yes, we're back. The first thing is that if we consider now units, we might measure length in meters and time in seconds. Can you add meters to seconds? Obviously, you cannot. So you'd have to be able to add seems that we're working again. So, and you can't add or subtract meters from seconds and vice versa. You can only add the same units. In mathematics, they're just numbers, so if you've got no units to them, x's and y's, etc. But in physics, we want units. There are unitless quantities, constants and such, but there are also constants that have units. So units are very important to physics. And strictly speaking, an equation needs to be, the left-hand side needs to have the same units as the right-hand side. And a diligent engineer and scientist would make sure that they've got meters on one side if they want meters, and the other side of their equation has also got meters, because if they have meters equal to seconds, there's a bit of a problem. So ultimately, they're different dimensions. So if we go back to our generic dimensions, length can't be added to time, and vice versa. But we already live in a 4-dimensional world because we've got length, three sets of them, length, breadth, and height, all units of length, and we have time. So we already live in a 4-dimensional world in this sense. But in Einstein's world, length and time, the 3 lengths, x, y's, and z's, for instance, and time, are jumbled up together so that you have a 4-dimensional time in which you can add and subtract all of these quantities in one equation. So let's have a look at how we can denote a position in place and time, where we'll have x as the length, y as the breadth, and z as the height, and we'll have t as time. So a time and place can be specified by a set of coordinates, x, y, z, and time. For instance, if you say to your friend, I'm going to meet you at the cafe for a coffee at 1 o'clock. Well, if you go there at 5 o'clock, are you likely to encounter your friend? Probably not. And if you decided that you didn't like the x and y, z coordinates and you went to a different place, you probably wouldn't meet your friend either. So you have to go there, x, y, z, the right coordinates for the place, and at the right time. So we already live in a four-dimensional world. So there's nothing new in Einstein's idea of nothing new in the idea of a four-dimensional world in the terms of Einstein's conception of the universe, because we already have that. What is different is that you cannot jumble up X, Y's, and Z's and T's. Jumble up time and space together, which is what he has done. So, for instance, the distance between 2 points depends on X, Y's, and Z's. It doesn't depend on time. The difference between Phoenix and, I don't know, LA, the distance between there is X, Y's, and Z's. But it's not a question of time. Now, that means that the four-dimensional world in which we live, as modelled by Newton, is consistent with Newton. So we'll have now a look at Cartesian coordinates. I'm sure you're all familiar with this from school. Usually we'll have the Cartesian plane, X and Y. Here we've added the Z, so we have space. But it's just like the corner of a room. For instance, if you look at any corner of this room, because it's a rectangular building, we have an X, Y, and Z set of coordinates immediately before us. And they are all perpendicular to one another. Not only that, they're independent of one another. So that any distance along, well, X, Y's, and Z being perpendicular, they don't have components in each other's directions because they're definitions. So now I want to look at a right triangle, and we see how the jumbled up nature of time and space is based on an error utilizing right triangles. So we quickly revise the theorem of Pythagoras, and I'm sure you will remember that if you construct a square on the x-axis, as I've drawn it in this diagram, and a square on the y-axis, we have areas of those squares, x squared and y squared, from simple geometry. And then you'd construct a square on the hypotenuse of the right triangle, then we find that x squared plus y squared equals r star squared. Well, that's just the area of two squares added together give you the area of another square. And usually in geometry in school, the squares are dropped off, and we just say x squared plus y squared equals r star squared, or whatever you want to give a label to the hypotenuse of the right triangle. But this is the theorem of Pythagoras. But I ask you, let's consider this. R star is not a new dimension because it's composed of x's and y's. So it's not a new dimension, it's not perpendicular to x and y. It's a function, if you like, of x and y. It's determined by x and y. Now we'll consider a circle, and we'll draw the circle around the right triangle. The right triangle hasn't changed, but now we can reinterpret the length of the hypotenuse of the right triangle as the radius of a circle. It goes through the end of the hypotenuse, where the hypotenuse has its origin at the origin of the coordinates, where x and y is 0. And again, by the theorem of Pythagoras, because it's a right triangle, x squared plus y squared equals r star squared. Now you can see why I labelled it r star, because to give you the idea, it's also the radius of a circle in this circumstance. Now, is the hypotenuse of the right triangle in this instance perpendicular to x and y? No, it's still the right triangle. And can x squared plus y squared minus r squared equal 0 never be not equal to 0? This is an important point. We can see that it must always be 0 because x squared plus y squared equals r star squared. So if you subtract r star squared from each side, you must have 0 on the right side, and it's always 0. Unless, of course, you're a cosmologist, which I'll come to shortly. So x and y stay perpendicular to one another, and even in this last equation, x squared plus y squared minus r star squared equals 0, the r star is not perpendicular to x and y. Now let's go from the two-dimensional to the three-dimensional. This is a sphere. Again, our right triangle is present. Notice that in this case, by the theorem of Pythagoras, if you look in the xy plane there, x squared plus y squared equals r star squared. That's the same triangle we've been talking about. Now, if we go from the tip of the hypotenuse and go into the z direction, the length r from the origin to the surface of that sphere is r star squared plus z squared. And we know what r star squared is, so we'll put that into the equation and we get x squared plus y squared plus z squared equals r squared. Again, we've applied the theorem of Pythagoras. So the quantity r in three-dimensional space is not perpendicular to x, y, and z either. And again, if I take r squared from both sides of this equation, I get x squared plus y squared plus z squared minus r squared equals naught. Can it ever be anything other than naught? Of course it cannot. Again, unless you're a cosmologist, which I will show you shortly. But before I go to that interesting point, let's revise what we know about speed. What do we define as speed? It's the distance that something moves in a certain time. And we take the ratio of the distance to the time that gives you a speed. So in the case of the hypotenuse of that right triangle, in the sphere that I drew in 3 dimensions, the distance from one point to the other point, or from between the two ends of it, is the square root of x squared plus y squared plus r squared, because, sorry, x squared plus y squared plus z squared, because r squared is the square of the distance. So the length of the hypotenuse is not r squared, that's the area of the square that we drew on it. So the length of the side of the square is r. So we take the distance, x squared plus y squared plus r squared, I'll say that again. X squared plus y squared plus z squared, take the square root of it, that's the distance, we divide it by time, and that can give us a speed. And again, if we use that the distance that, for instance, that light travels some distance, and the time that light travels that distance, and we take the ratio of that, we have the speed of light. Just as though you had the speed of a truck. If a truck goes from A to B, and it travels that distance in a certain time t, well, you can calculate its speed. Well, it's the same with light. Instead of the speed of the truck, we put in the speed of light. So we conclude from this that so that neither Vt nor Ct, now Vt is a distance. So if I say to you, you're traveling at 60 miles an hour for 1 hour, how far did you go? Well, you take the speed, you multiply it by the time, and you get the distance. In that simple instance, it's 60 miles per hour times 1 hour. The hours cancel out, and you've got 60 miles. So Vt and Ct is not an independent fourth length dimension. It's just how long did it take to travel along the hypotenuse of a right triangle? Unless you're a cosmologist. Because the space-time concept associated with Einstein and Minkowski, it was actually introduced by Minkowski in 1907 and enthusiastically adopted by Einstein and all his followers ever since. So now you've got a four-dimensional space-time continuum that has curvature. So space-time requires Ct to be an independent fourth length dimension, because C times t, that's a distance. Now we can add that distance to other things. If you have a distance, you can add it to distances. This is how time is snuck in to an equation to jumble up space and time and give you the idea of space-time. Well, it's not. It's just some kind of space with all length dimensions. So mathematically treating C times t, or V times t, as the speed of a truck times the time it travelled, does not make it, or mathematically treating it as such, does not make it so, and does not make t an independent fourth length dimension. Ct is not a fourth length dimension, Vt is not a fourth length dimension, and t on its own, they can't even be a length. So we're going to go to the truck that I was talking about. Let's consider a truck moving along the hypotenuse of the right triangle from A to C. Now, there are two ways you could get from A to C. You could go along the x-axis at some speed. You could go then along the y-axis at some speed, and you get there. But the shortest distance, of course, is along the hypotenuse, as we know from elementary geometry. So let's have a look at this. A truck has a constant speed along r star is v. In time t, it travels from A to C along this hypotenuse of a right triangle. Then the theorem of Pythagoras applies, and we say r star squared is equal to v times t squared. And that's equal to x squared plus y squared. And that means that v times t is equal to the square root of x squared plus y squared. That's the length of the hypotenuse of a right triangle. And still, r star equals v times t is not a new dimension. And it's not orthogonal to x and y. So we write the equation of this right triangle as x squared plus y squared equals v squared t squared. Well, recall, we could draw a circle around that, and that would make it the radius of a circle. And if we subtract v squared t squared from both sides, we still get x squared plus y squared minus v squared t squared equals 0. Can it ever be other than naught? Well, it's the right triangle. The answer is it cannot. Again, unless you're a cosmologist. So now we'll go to the three-dimensional analog, because it's actually the same diagram, except I've drawn a circle or a sphere around the right triangle. And everything else applies in the same way as we did with the right triangle in the sphere before. So instead of r squared, well, a truck travels from A to D at some speed v, and so the distance along there is v times t, and the x squared plus y squared plus z squared equals v times t all squared. Well, as we had before, x squared plus y squared was equal to r star squared or v squared t squared. That was the equation also of a circle. So the equation for the length of the hypotenuse of the right triangle also gives us the radius of the equation for a circle. Here, we have the length of the hypotenuse is also giving us the equation for a sphere. So right triangles are very important. And again, we can write x squared plus y squared plus z squared minus v squared t squared equals naught. It's always naught. And it's not orthogonal to x, y, and z. Unless you're a cosmologist. So we see that space-time is not a 4D continuum. Let's replace the truck that was moving along from A to D by a light ray. Everything is exactly the same as before, except now the speed is not the speed of a truck, it's the speed of light. So the truck's not going from A to D, a light ray is going from A to D. Does anything else change? Not at all. And so now we come to what the cosmologists do, following Minkowski and Einstein. So for the right triangle, x squared plus y squared plus z squared minus c squared t squared equals 0 always. So it can never be not equal to 0, and it can never be orthogonal to x, y, and z. It's always the hypotenuse of a right triangle. So if you take away the sides of the triangle and just leave the radius line, does it change anything? No, it doesn't. It's still the hypotenuse of a right triangle, but we don't have the right triangle there anymore. And with the right triangle disappeared, magic is done. Because cosmologists write x squared plus y squared plus z squared minus c squared t squared equals s squared is not equal to naught. And equal to naught is a special case, according to them. According to Albert Einstein and Hermann Minkowski. But this is clearly a violation of elementary geometry. All right? Now, the fundamental reason why they start writing this s squared not equal to 0 is because they mix it up incorrectly with what's called Riemannian geometry. But if you want to have a four-dimensional space in pure mathematics, you have to have four independent quantities. Well, x, y, and z, as we see by looking up at, say, the corner of one of these corners in this room, you have x, y, and z. They're independent of one another. But we see that the speed between any points in that space is not independent, because you need the x, y's, and z's and the time to be able to calculate the speed. So it's not independent. The speed is not independent. If I multiply speed by time, the very same time I use to calculate the speed, that's not independent either, because it's the length of the hypotenuse of a right triangle. So to do four-dimensional mathematics, you need four independent quantities. Well, c times t is not an independent quantity. Treating it as an independent quantity by saying, well, we'll make it equal to s squared, not equal to naught, doesn't make it true. It means you made a mistake. The length ct, well, what is its units? Or rather, what is its dimension? It's speed times time. So speed is length divided by time, and then we multiply that by time. Well, t cancels out. One's in the numerator, one's in the denominator, and we're left with length, obviously. So just because you've got length out of some quantity doesn't mean that you've got a new dimension. For instance, if I multiply x by y, I get length squared. And if I divide it by z, I get length squared divided by length. That gives me length. Is xy over z a new dimension? Not at all. Similarly with x squared over y, or x squared plus y squared, well, x squared plus y squared still has the units of length squared, or the dimensions of length squared. So if you had meter squared plus meter squared, you still got meter squared, or if you got length squared plus length squared, you still got length squared, because it's not a change in any unit. And if you divide length squared by length, for instance, x squared plus y squared divided by z, you get length. Did I just make a new fourth independent dimension orthogonal to the x, y, and z? Not at all. And finally, if I take x squared plus y squared plus z squared and divide it by x or y or z, I still get the dimensions of length, but I did not create a new dimension. It's not a new dimension that's not orthogonal to x, y, and z, unless you're a cosmologist. I know it's a bit of a tiring refrain, but we need to remind ourselves what cosmologists do, so we never lose track of that. So I ask you now, if I have x, y over z, is that the length of anything? What is it the length of? We've got our x, y, and z coordinates. I take x, y, and I divide it by z. What's that the length of? It's not in the length of anything. It has dimensions of length. There's a formal mathematical relationship, but what is it the length of? It's not certainly not the length of a hypotenuse of a right triangle, and it's not the length of x or a y or a z. It's just some combination of x, y's, and z's to produce length. But it's not a new dimension, and it's not orthogonal to anything of those new dimensions. It's just nothing. It's not the length of anything. And is it perpendicular to the x, y's, and z's? Well, no. So it's neither perpendicular to anything, and it's not the length of anything, even though it has the units of, or the dimensions of length, and it's made up of the x, y's, and z's. So combinations of x, y's, and z's don't give us new dimensions. So we come now to Einstein's fantastic clocks. Now, we'll bear in mind the things that I've covered here when we get to space-time itself. But before we do that, we want to talk about, I like to talk about Einstein's fantastic clocks. And in his famous 1905 paper, Einstein defined time by means of these fantastic clocks that he concocted. I'll read to you what comes from his 1905 paper, the so-called seminal work that turned physics into a completely new paradigm. It changed our conception of space and time. Well, it ruined our conceptions of space and time by turning it from physics into a fantasy land. Here's what Einstein says: thus, with the help of certain imaginary physical experiments, we have settled what is to be understood by synchronous stationary clocks located at different places, and have evidently obtained a definition of simultaneous or synchronous and of time. The time of an event is that which is given simultaneously with the event by a stationary clock located at the place of the event. This clock being synchronous, and indeed synchronous for all time determinations, with a specified stationary clock. Well, if you can make sense of that, that would be a miracle. But, let's see now. There are a number of points I want to make about this. The first thing is he wants systems of stationary observers holding clocks that can all be synchronized. In other words, they all read the same time. So he wants systems of clock-synchronized stationary observers. That's what he's saying there. Right? The other thing is he says he defines time. Well, I'll ask you something. Do clocks define time? Do they define time? Clocks no more define time than a pressure gauge defines pressure. A speedometer defines speed, a thermometer defines heat, or a spring defines gravity. Because if time is defined by a clock, well, all those other things must be defined by the measuring instruments. But measuring instruments are invented to do what? To measure something other than themselves. If a measuring instrument measures only itself, It's pretty hopeless. Einstein's clocks measure only themselves. He has dispensed with physics, something external to the measuring instrument, and defines time in terms of his clock. Now his fantastic clock can do whatever it likes, independent of any physical reality, and thereby warp stuff. Let's have a look at how he sets up clock synchronizations. We'll read again from Einstein so there's no doubt. We have so far defined only an A time and a B time. He's got a time at A and he's got a time at B, righto? We have not determined a common time for A and B. This is where he wants to get his synchronizing clocks, right? For the latter cannot be defined at all unless we establish by definition that the time required by light to travel from A to B equals the time it requires to travel from B to A. You go from A to B, then you travel from B to A at the same speed. Well, it should take the same time. Let a ray of light start at the direction of A and arrive again at A at the A time t primed A. In accordance with the definition, the two clocks synchronize if TB minus TA equals T primed A minus TB. In other words, if you go from A to B and it takes a certain time, you go from B to A at a certain time, travelling at the speed of light, they must read the same times. That's his way of setting up clocks. In that little diagram, you go from A, you go to B, then you go from B back to A, and you see that at A you start at TA, you get to T, you get at B you get TB, and then when you get back to A, you're at T primed A. Now he goes to, as you see, a great pains to define what he means by clock synchronization. This is only part of it. This is the part that I wanted to talk about. Now, to emphasize again his systems of observers, what do we see from his earlier statements? He wants systems of clock synchronized stationary observers. Okay, that means everybody in this room who's sitting there, you're not moving anywhere, and you're all holding a clock, and we want to make sure all your clocks are synchronized so that everybody says, yes, I've got the same time, even though you're in different places. Well, that's reasonable. We want that. Experience tells us that's what we need. Einstein says, let the time t of the stationary system, now he's got a system of stationary observers, and they're all got the same time. So he's got now, let the time t of the stationary system be determined for all points thereof, at which there are clocks by means of light signals in the manner indicated in section 1. That's his elaboration on how he's going to synchronize his clocks. Send a light ray from A to B comes back, we have this relationship, and that's it. Similarly, let the time tau of the moving system. So he's got first a system of stationary observers and with all their clocks, and then he's got another system over here, one's T and one's tau for their times. So he's got now, okay, he says here, where we are, I've lost my place. I'll go back and read anyway. Similarly, let the time tau of the moving system be determined for all points of the moving system at which there are clocks at rest relatively to that system by adopting the method given in section 1 of light signals between the points at which the latter clocks are located. To any system of values x, y, z, and t, yeah, that's one system, which completely defines the place and time of an event in the stationary system, Einstein calls that a stationary system, there belongs a system of values xi, eta, zeta, and tau, determining that event relatively to the system K. So if we have X, Y, and Z associated with a system big K, and the Greek letters for the system little k, his big K system's moving, and his little k, or his big K system is stationary, and his little k system is moving. But according to him, you can switch it around. The little system K could be stationary, and the other one could be moving because it's only relative motion. Now, however, as we know how to judge whether two or more clocks show the same time simultaneously and run in the same way, we can very well imagine as many clocks as we like in a given CS. CS is coordinate system. Each of them will help us to determine the time and events happening in its immediate vicinity. The clocks are all at rest relative to the coordinate system. They are good clocks. What is a good clock? Maybe they were made by the Swiss. They make good clocks. And are synchronized, which means that they show the same time simultaneously. Well, all of this long-winded stuff. It says you're all sitting in the room and you've all got a clock where you've all got a watch. That's a clock. And you've all got them synchronized, so you read the same time. That's all it means. All of this just means that. But you've got two systems. So there's another set of people in another room, the same size as this. They call their clocks readings Tor. You call your clock readings T. They call their positions Z, Eta, and Zeta, and you call it X, Y, and Z. That's all. So now we have his systems, Einstein's systems of observers. There are two systems, all having the properties we just spoke of, big K and little k. Einstein likes to keep his little k, the moving system, and his big K, the stationary system. But as I said, you can switch it around. It doesn't matter. So in the left-hand diagram, K and K, there's no motion between these two systems of stationary clock synchronized observers. And in the other two, they are moving. Well, Einstein keeps K, capital K, as his stationary system, and he says that the little k is the moving one. Well, if it's moving to the right in the middle one, K is moving to the right with respect to K, big K. And on the final diagram, little k system, the whole system is moving along to the left at some speed, v. Well, that's minus v according to K, because it's in the opposite direction. And Einstein's systems of observers K and K are both clock synchronized and stationary. Within their systems, right? They are not clock synchronized and stationary with respect to one another, those systems, because one system's moving with respect to the other one, so it's not stationary. But if you're in one of those systems, all your points are stationary and all your clocks are synchronized. So if you're the one in little k and I'm the one in big K, all my clocks are synchronized and all the points on the x-axis are all stationary. And in your system, all your clocks on the z-axis are stationary and all your times Tor are synchronized. Einstein's systems of clock synchronized stationary observers are an essential feature of special relativity. He holds that the Lorentz transformation associates coordinates x, y, z, t of his stationary system K. Yeah, we'll look at the bottom system of observers. They're all stationary and they're all reading the same time. With the coordinates z, eta, zeta, and Tor of the moving system. That's the little system, little k system at the top. So the little k system's moving, producing time dilation and length contraction. A system of clock synchronized stationary observers, little k, when at rest, is not clock synchronized when they are all moving together or all move together with respect to a clock synchronized stationary system K. So in other words, if you're in the K system or the big K system where all your clocks are reading the same time and you look at the clocks as they all pass you, held by other stationary systems in their system, it all goes haywire. All the clocks are all reading different things. So it becomes mind-boggling. So now we're going to look at the Lorentz transformation. The Lorentz transformation is on the left. This was first introduced by Waldemar Voigt in 1887. He didn't have the term beta. That's the only difference. The beta term, which is 1 over the square root of 1 minus v squared over c squared. This term did not occur or did not appear in Voigt's transformation. So if you take beta out, you have Voigt's transformation. Subsequently, Poincaré, the French mathematician, Lorentz, the Dutch physicist, and Einstein, they adopted Lorentz transformation modified by this effectively constant beta, because v is moving, or the value of v is a constant. It's the relationship between the two moving systems is such that the speed v is a constant. That means beta will be a constant. For any given value of v, well, c is fixed because it's the speed of light, so v over c and v squared over c squared, that's some constant, and we have a constant beta. Now, let's eliminate from the x from the equations for the Greek ones, the little k, t. We eliminate x So we solve this equation here, the second equation for x, we get the result, and we stick it into the top equation. And we get tau is equal to t over beta minus zv over c squared. It's just a simple bit of algebra. You could do it, but we won't bother with the details here because you could do it yourself. And if t equals 0, tau equals 0. So in other words, if tau is equal to t over beta, that happens when z is 0. Because if you look at the top equation, set z equal to 0, you get tau is equal to t over beta. And then if t is 0, tau is 0. So if you've got z equals 0, then you can have t equals 0 and tau equals 0. That's what Einstein wants to do. He wants to make sure that the two origins coincide at the time t equals 0. As they go past one another. But if t equals 0, if t equals 0, you can just put in t equals 0 in the top equation. You get tau is equal to minus z v over c squared. Professor Wolfgang Engelhardt wrote a paper in 2016, late last year, where he points this out. And you see that, well, tau now is a function of position z. That's supposed to be the time of all the clocks in the stationary system. So if t is 0, tau does not necessarily 0. Which means that since we're talking now here only about the system itself, all the coordinates in the moving system itself, all the positions in that system have different times. Right? So that means Einstein's idea of having clock synchronized stationary systems actually fails. Because he wants to have t equals 0 at tau equals 0, but if we make t equals 0, we don't necessarily get tau equals 0. Why? Because you also have to specify that z equals 0. But that's the position in the moving system. So you see that the idea of having clock synchronization in the moving system fails. Because in that instance, as Engelhardt has pointed out, all the taus are different, depending on different positions. So we see, by using the Lorentz transformation on the previous slide, Einstein's clock synchronization doesn't hold unless t equals 0 and z equals 0. Well, that's a special case. Here's his logical error. Now, when I read Engelhardt's paper, I could see immediately that I could generalize it because Professor Engelhardt just had t equals 0. I said, well, let's make tau equal 0. Then we find for any time t in the stationary system, there is always a place z in the moving system where the time is always 0. Well, that violates Einstein's idea. Thus, for every t greater than 0 of the stationary system k, there exists a point z greater than 0 in the moving system little k where tau is 0. But they're both supposedly starting off at 0 and counting. Well, if you're both counting, you get bigger than 0. But here we show that you can always find a place where it's still 0. But according to Einstein's clock synchronization, this must be impossible. Einstein's synchronization is inconsistent with the Lorentz transformation. This is a logical inconsistency in the theory. If you have a physical theory that has logical inconsistency, is it valid? No. If you have a physical theory that doesn't accord with the experiment, is it valid? No. So there are two things that a physical theory must have. It must have logical consistency and accord with experimental reality. If it fails on either one of those, it fails absolutely. Well, here's a logical problem. It gets worse. This is just the key to the door. So we see that Einstein's clock synchronization is inconsistent with the Lorentz transformation. But he wants to make everything consistent with the Lorentz transformation. He didn't. Let's have a look at systems of stationary observers. So I ask a question. Are systems of stationary observers satisfying the Lorentz transformation clock synchronized? In other words, if I set up a system of stationary observers, I make them satisfy the Lorentz transformation, must they necessarily come out to be clock synchronized as Einstein wants them? The answer, well, the answer is no, because we just proved that in the previous two slides. Now we can construct some counterexamples. Let's construct a system of stationary observers, which means that they don't change with time. All the x's are not dependent on time. They're stationary. I'll take a real number sigma, and I'll put a subscript on an x, and I'll say x sub sigma equals sigma x sub 1. X sub 1 greater than naught. So if I give you an x sub 1, and you have sigma, which is a real number, you can say x sub 1 is located here on the x-axis, and all the others are now specified immediately by some value of sigma that you can put in, because sigma is a real number. So we have a system now of observers that we have labelled, each one of them. And so we can refer to each one of them and see what they see, as opposed to just calling it x and never knowing which one we're talking about, which is what Einstein does. Each observer sigma at position x sub sigma reads its own clock, time t sub sigma. So x sub 1, you see there, x sub sigma, they're located on the x-axis, and they're stationary. So if we use x sub sigma equals sigma x sub 1, and the first equation of the Lorentz transformation, which was 3 or 4 slides ago, and we stick it in there, there's only one way we can ensure that we get consistency of the Lorentz transformation. And we get this equation for the times. T sub sigma equals T1 plus sigma minus 1 V x1 over c squared. If I put sigma equals 1, what do I get? T sub sigma equals T sub 1. That's one case. If any other value of sigma, the times are not the same. In other words, if they are systems of stationary observers that satisfy the Lorentz transformation, they cannot be clock synchronized. Here's an equation that I derived in a paper that I wrote, but I've just given you the result rather than the derivation. If you put sigma sub sigma equals sigma x sub 1 and t sub sigma into the second equation of the Lorentz transformation that we saw earlier slide, we get this complicated looking expression. And again, if we make sigma equals 1 in that bottom side equation, sigma equals 1, then we get 1 minus v squared over c squared plus v squared over c squared. That's just 1. And that produces x1 minus v t1 multiplied by beta. That's exactly the Lorentz transformation in one particular case, Einstein's case. So we'll draw up a little graph here, or a little table of things. We've got sigma on the left, various values. You can put any values you like. I've put in a few. X sub sigma, T sub sigma, Z sub sigma, and tau. Well, you see, tau comes out to be the same. But that's not synchronized in the moving system. That's what the stationary system sees when it looks at the moving system. The moving system's going past. It looks at the system and says, well, all those clocks are in sync. But all the clocks in my system or your system that's watching it are not in sync. They can't be clock synchronized. Now we can invert it because it's symmetric. In the other system where you're looking at the clocks, they're all sync. If you're in that system looking at this system, you say, well, all my clocks are not sync, but the ones in the other one that's moving past me are in sync. Well, that's completely opposite to Einstein's. Remember the diagram, all the ones on the bottom were all in sync, and the ones that were moving past were all out of sync. Here we got the opposite. So this is the stationary Lorentz transformation. In other words, this is a system of equations that is for stationary systems of observers that satisfy the Lorentz transformation. You can see here that the time cannot be synchronized. But if I make sigma equals 1, everything reduces to the simple expressions that we started with. So I said here, setting sigma equals 1 in the stationary Lorentz transformation, the Lorentz transformation used by Einstein is recovered. However, a system S that contains only one observer cannot, by its singular character, synchronize its clocks with anything or judge simultaneous events in S. Einstein incorrectly permitted his privileged observer, sigma equals 1, to speak for all observers, thereby violating the fundamental tenet of his theory that no observer is privileged. In other words, he had a tacit assumption that he could construct systems of clock-synchronized stationary observers with the Lorentz transformation. We see that it's only true in one case, sigma equals 1. But in that case, it's the only one in the whole system. There are no others in the system. Can it synchronize with anything? No, there's only one clock in the system itself. Can it measure distances? No, because it's only one point. It's like taking the point out of the whole x-axis and looking at the point itself. The other x-axis, the rest of it has disappeared. so it can't measure distances or anything. And it can't be privileged because Einstein requires that they're not privileged. That's why he wants whole systems of clock-synchronized stationary observers. No one's privileged. This is the inverse transformation. I just put it there for content. Now we look at clock-synchronized systems. So I asked the second question. Are systems of clock-synchronized observers satisfying the Lorentz transformation stationary? The answer is no. We can construct counterexamples here by taking the Lorentz transformations, and we insist that all the clocks in the capital K system read the same time t. So that's on the left. And the only way to do that is using the Lorentz transformation is by setting that equation up. Then we ensure that every clock in one system is synchronized. So they read the same time. Can they be stationary? Well, we see here that when we solve it all, we get for x sub sigma, they're all functions of a time. X sub sigma equals 1 minus sigma c squared t over v plus sigma x1, where x1 is greater than 0, but arbitrary. Now we see that x sub sigma is a function of time. That means it's not stationary. So although all observers in K are clock synchronized to a common time t, only x1 is not a function of the time t. Yeah, if I put sigma equals 1 in, I get x sub 1 is equal to x1. And that's not a function of time. That's Einstein's privileged observer. 1 in a set of how many? Well, they're infinite sets. So he has one element out of an infinite set, not the infinite set, and he takes that one element and allows it to speak for the whole infinite set of observers. That's wrong. Here we see counterexamples. Here's the Lorentz transformation for clock-synchronized observers. Notice that sigma can only have limited values. It's not the whole set of real numbers. It's only 1 minus v over c is less than sigma is less than 1 plus v over c. And if v is 0, we get 1 is less than sigma is less than 1. That just means it's 1. Einstein's observer again. So if we set sigma equals 1 in the clock synchronized system, we recover the Lorentz transformation used by Einstein. It's a privileged observer. He's not allowed to have that because he says we don't have privileged observers. It pertains to only one observer in system K and one observer in system K, little k. By tacitly assuming systems of clock-synchronized stationary observers consistent with the Lorentz transformation, Einstein incorrectly permitted his privileged observer sigma equals 1 to speak for all observers, thereby violating the fundamental tenet of his theory that no observer is privileged. This is the set of equations for the inverse clock-synchronized Lorentz transformation, again for content. Now, Lorentz invariance. According to the cosmologists and Einstein and Minkowski, remember when we did the right triangles in the spheres, and we had x squared plus y squared minus z squared plus z squared minus c squared t squared equals 0? Well, Einstein requires that no matter how the systems are moving, they all must come out with exactly the same equation, the only change being the symbols. And he calls this, or this is called Lorentz invariance. So they require this top equation. So when you change from the x, y, z, and t to the Greek ones for the moving system, you get the same equation. Well, we remember that that's always naught. Cosmologists think that that's not always naught. So, but by the Lorentz transformation, we have x and y y and z don't appear, they're 0, because everything's moving along the x-axis. So we can make that 0, and we can therefore reduce the equation to a simpler one. X squared minus c squared t squared is equal to the c squared minus c squared tau squared. But if we substitute now the findings of the previous slides for the stationary system, we get this complicated expression. And this is true for all values of sigma. So, Lorentz invariance is maintained by the counterexamples that I've constructed. Well, we expect that because I constructed it using the Lorentz transformation. So we would expect it to have Lorentz invariance. That satisfies Einstein's requirement. But again, this is not a single observer, it's many observers, it's an infinite set. Now here's the same relationship for the clock synchronized Lorentz transformation, and we get that expression. I'll go back to the other one. There's the expression for this. And there's the expression for this system. And again, we see when you put all the things in there, you get Lorentz invariance. The only change in the equation is the symbols. That's what he wants. So the counterexamples satisfy that condition. Now we compare the observers. Let's take the stationary Lorentz transformation relation that before and equate it to the clock synchronized Lorentz transformation. They're not the same unless sigma equals 1. So if I put in sigma equals 1, this becomes an identity. Because in any other case, they're not equal. They satisfy the Lorentz invariance individually, but when they're equated, they only hold when sigma equals 1. That's Einstein's privileged observer, which he allows to speak for all elements of the infinite set of observers. And that's his mistake. So Einstein's system of clock-synchronized stationary observers holds for only one observer. No other observers are equivalent. Thus, Einstein's tacit assumption is false, and the special theory of relativity is false. Here's a wave equation. This is a simple wave equation. It's a sine wave. This is a little bit more complicated because now we have a differential equation. The wave equation, the standard wave equation, electrical engineers, I'm sure, are familiar with this because it's related to electromagnetic radiation. So if we have a wave polarized in the y direction traveling in the x direction with speed c, this equation describes it. It's called the standard wave equation. Right? This is a one-dimensional wave equation as opposed to a three-dimensional wave equation. So I don't expect you all to understand that, but the point of it is we have a nice little sine wave here. That's a wave equation. It's a plane wave. So now, special relativity requires the wave equation to be invariant under the Lorentz transformation. In other words, the equation, when you put in the Lorentz transformation on the left-hand side equation, you get the right-hand side. It's exactly the same equation, except that you've just changed the symbols. So now the standard wave equation becomes invariant between moving systems, systems that are in constant rectilinear motion. This is what Voigt wanted to do in 1887 for reasons that are only known to Voigt because it doesn't make sense. So using the standard, or using the stationary Lorentz transformation, I take the counterexamples that I've constructed and I put it into the standard wave equation and I get the thing on the right. This is invariant only when sigma equals 1. Again, Einstein's privileged observer. If you put 1 in there, you see, it comes out to be the standard wave equation. Otherwise, it is not. So the idea that the Lorentz transformation makes the standard wave equation invariant under its transformation is patently false. Voigt was wrong, and hence Poincaré was wrong, Lorentz is wrong, and Einstein wrong. But this is central to special relativity. Without it all, special relativity is a dead duck. Here now I'll use the clock-synchronized Lorentz transformations. We get exactly the same equations. Again, sigma equals 1 is the only one that makes it invariant. That's Einstein's privileged observer. He doesn't know what he's done. He takes this privileged observer and he lets it speak for all of them. So now he thinks he's got clock-synchronized systems of stationary observers. When he doesn't, he only has 1, and 1 is meaningless. So we compare the wave equations. They are the same only when sigma equals 1. Comparison of positions and times, they are the same only when sigma equals 1. So we now conclude. Systems of clock-synchronized stationary observers are inconsistent with the Lorentz transformation. Einstein's theory of relativity is therefore logically inconsistent. It is therefore false. And the Lorentz transformation is meaningless because it does not do what it says or what it claims that it can do. It does not. And so that concludes my rather technical discussion, proving that the special theory of relativity is a fairy tale. Right? Thank you for your time.